Hello students and welcome to Chemistry A. I'm Ms. Slate and today we're talking about waves. So the two main parts of a wave that we really care about are wavelength and frequency. Wavelength is defined as the distance from crest to crest or trough to trough on a wave, and it's typically measured in units of meters. So you can see in the image they're measuring the wavelength from crest to crest, crest meaning the highest point of the wave. Wavelength, on the other hand, is the number of waves that pass a point in a certain amount of time. And frequency is measured in units of hertz, where 1 hertz is equivalent to 1/seconds. And in this image, consider that all three of those waves are representing the same interval of time, and you can see that the low frequency wave has just a few waves in that time interval, where the high frequency wave at the bottom has many waves in that same time interval. Wavelength and frequency are also related to each other. Wavelength is inversely proportional to frequency. And hopefully this graph looks similar to ones that we created during our wave activity. This is symbolically how you would represent the statement, wavelength is inversely proportional to frequency, where wavelength is represented by the Greek letter lambda. It kind of looks like a funky H. And frequency is represented with the Greek letter nu. That kind of looks like a V with a handle on the left side. Wavelength and frequency can also be related to each other by wave speed, where the speed of a wave is equal to its frequency times its wavelength. Particularly in this class, we're going to be mainly concerned with light waves. So when we talk about the speed of the wave, we're going to be specifically using the speed of light in a vacuum. So c will always be 3.00 times 10 to the 8th meters per second. And again, when we're using this equation, because we're using a speed of light in meters per second, our wavelength always needs to be in units of meters, and our frequency always needs to be in hertz. Again, hertz being 1/seconds. So when you have to solve a wave speed equation, make sure before you start putting things into the equation that wavelength is in meters and frequency is in hertz. Because sometimes you'll be given wavelength in units other than meters. It might be given to you in kilometers, it might be given to you in nanometers, but before you put it into this equation, it needs to be in units of meters. Example number 1 says, what is the wavelength of a microwave with a frequency of 3.44 times 10 to the 9th hertz? Well, remember our equation that relates wavelength and frequency is the speed of a wave is equal to its wavelength times its frequency. In this case, we want to solve for wavelength specifically. So the first thing I'm going to do is rearrange this equation so that it solves for wavelength. To get wavelength by itself, I'm going to divide each side of the equation by frequency. So we get the equation, wavelength is equal to the speed of light divided by frequency. The speed of light is a constant, 3.00 times 10 to the 8th meters per second. Our frequency is 3.44 times 10 to the 9th hertz. Remember, hertz is the same as 1/seconds, so the hertz and the seconds are going to cancel when we do this mathematically. Also remember, the speed of light is a constant, and so on the test, you will always be given constants. You will not be expected to memorize them. Lastly, we just put this in our calculator. And we get a wavelength of 0.0872 meters, or if you put it in scientific notation, 8.72 times 10 to the -2 meters. Both of those would be acceptable as correct answers in this case. Typically, you don't need to put anything in scientific notation unless we're greater than times 10 to the 3rd or times 10 to the -3rd power. I rounded this answer to 3 significant figures. because our original frequency has 3 significant figures in it. Remember, anything that's a constant, like the speed of light in a vacuum, is considered to have infinite sig figs. So we would never base our sig figs off of a constant. Example number 2 says green light has a wavelength of 4.90 times 10 to the negative 7th meters. What is the frequency of the light? Well, once again, wave speed equation is what relates frequency and wavelength. In this case, I'm looking for frequency, so I'm going to solve the equation for frequency by dividing both sides of the equation by wavelength. So we get the equation, frequency is equal to the speed of light in a vacuum divided by wavelength. Speed of light in a vacuum is 3.00 times 10 to the 8 meters per second, divided by our wavelength of 4.90 times 10 to the negative 7th meters. The units of meters are going to cancel, and we get 6.12 times 10 to the 14th, 1 over seconds, or hertz, right? So typically we use hertz as our units for frequency, but if you wrote the units as 1 over seconds, that would also be accepted as correct units. Once again, I rounded to just 3 significant figures because our original wavelength had just 3 sig figs. And that is the basic of waves and the wave speed equation.